Okay, so any questions? If you remember, we were discussing mainly the Bose systems. Today we will continue with the boson systems, and we will be discussing what's called the Bose-Einstein condensation. In our last lecture, we were mainly discussing the photon gas and the phonon gas, which are systems in which the chemical potential is zero. So since the number of phonons or photons is not conserved, they can be absorbed and emitted. We cannot impose any restriction on their number, and hence there is no need for this Lagrange multiplier, which, if you remember, we had defined the mu as a Lagrange multiplier to impose the constraint on the average number of particles in our system. But for a general case, for example, if you take the helium is a boson, so that's a bosonic system whose number is conserved, so there is a finite chemical potential. And in fact, any system whose number is conserved, we will have a finite chemical potential. And the chemical potential is defined through this equation. The number of particles we have should be equal to the number of single particle states. Of course, this is for the non-interacting systems, of 1 over Z inverse e to power beta epsilon minus 1. And Z is defined as e to power beta mu. This was our definition. And then we also had the logarithm of the grand partition function, which we had called the Q potential, which we can also, we had shown that this is equal to PV over KT. For such a system, this will be equal to minus sum over, again, the single particle states, of the logarithm of 1 minus Z e to power minus beta epsilon. Now, of course, the problem is how do we do those sums? But before doing that, let's see how the Z changes as we change or how mu changes as we change the chemical potential, as we change the temperature. Now, one thing you should note is, you see this number, 1 over Z to the minus 1 e to power beta epsilon minus 1. This was the average number in a given single particle state with an energy epsilon, and this should be larger than 0. So this basically tells me that for all epsilon, not just for a single one, for all the energy levels, this should be larger than 0. But this tells me that Z to the power minus 1 e to power beta epsilon should be larger than 1. Or if you use the definition of Z, this means that mu should be smaller than epsilon for all energies. And in particular, if you shift your energy level so that the ground state energy to be 0, this tells us that mu should definitely be less than 0 for bosonic systems. Now, if you look at one of those terms, with e to power beta epsilon minus mu minus 1. So for fixed mu, you see, if you would plot this as a function of energy, well, energy takes real values. The single particle energy states are real values, but we can just consider this as a function of epsilon. And then, okay, it has a pole. It diverges when epsilon is equal to mu, which is a negative number. And as epsilon increases, or epsilon minus mu increases, it starts decreasing and it goes to zero exponentially. It has such a behavior for a given value of t. Let's say t1. Now if we change t1, assuming again that mu is fixed, this graph basically, you see, if you lower the temperature t, then beta becomes larger. But beta becomes larger just means that this goes to zero faster. So for a lower t at fixed mu, it just tells me that the curve is below this one. So this is t2 less than t1. Okay, so if, of course, mu is constant. So this basically tells me that this sum, or NBE, is a function of temperature at fixed mu, is an increasing function. Of t, whatever the value of epsilon is. As long as mu is fixed, then this, if we lower the temperature, it gets smaller. If we increase the temperature, it gets larger. But that means that keeping mu fixed, we just cannot keep this sum fixed. You see, this sum should be fixed, whatever the temperature is, because the number of particles is independent of the temperature. So it basically tells me that if I change the temperature, I also have to change the mu. So the question is, in which direction should I change the temperature? Should I change mu? Well, the answer is already in this graph. You see, if I lower the temperature, now the graph moved below, but you see, wherever you put mu, it diverges there. So basically it tells me that at lower temperature, mu should approach positive energies. So that if I change the position of mu, let's say over here, this is mu prime, then mu prime, for this mu prime, at the temperature T2, my graph will look like this. Again, this is T2. So what this will tell me is that the number of particles at lower energy states increases if I make this modification, and the average number of particles in states with a higher energy decreases. Well, basically that's what I expected. So if I lower the temperature, more particles should move towards the ground state. So what all this argument is telling me is that mu increases as the temperature decreases. So as a function of temperature, we will see how it changes as a function of temperature. So as a function of temperature, first of all, at large temperature, they should have some negative value. And then as we lower the temperature, it increases. So as I said, the question is, when does it reach zero? If it reaches zero, at some value larger than t, so this is what's called Tc. If Tc is larger than zero, then we have what's called the Bose-Einstein condensation. Well, we will do it more formal treatment in a moment. But this is what we basically call the Bose-Einstein condensation. The defining property of Bose-Einstein condensation, let me say, one of the defining properties, that mu becomes zero. Now, let's go back on how we defined the mu. You see, this was the defining relation. N is equal to sum over the average number of particles, or this is equal to sum of 1 over z to the power minus 1 e to the power beta epsilon minus 1. Now, what we usually do is we just write this as an integral. Well, let's just do it again. So we say that, okay, this is equal to d cubed p, d cubed q over h cubed, in the classical approximation at least, times 1 over z to the minus 1 e to the power beta epsilon minus 1. And so this we can rewrite as, let's say, v from the q integral, assuming there is no potential, because if you have a potential, this treatment will be should be modified. V times 4 pi from the angular integral divided by h cubed times p squared dp 1 over z to the power minus 1 e to the power beta epsilon minus 1. Let's assume a non-relativistic gas. Well, eventually we will be looking at low temperatures. And for a non-relativistic gas, the energy of the particle is square root of 2m p, the momentum. So I'm trying to convert this to an integral over the energy. And so the epsilon will be square root of 2m over 2 square root of p. No, sorry. P is square root of 2m epsilon, so dp is square root of 2m over 2 square root of epsilon. So if we just put everything, so the total number of particles in my Bose system should be equal to v times 2 pi times 2m to the power 3 halves divided by h cubed times epsilon to the power 1 half, the epsilon from 0 to infinity times z to the power minus 1 e to the power beta epsilon minus 1. Or small n is equal to 2 pi times 2m to the 3 halves divided by h cubed, 0 to infinity, epsilon to the 1 half, the epsilon. Now this is how we had in fact defined the density of states. This A epsilon is 2 pi v 2m to the 3 halves divided by h cubed. Now there's a problem. You see the total number is given by this expression over there. You see, if you look at the density of, so here there is also epsilon to the power 1 half. You see, the density of states is proportional to square root of epsilon, which goes to 0 as epsilon goes to 0. So this basically means that in the total number of particles, you see the total number of particles is 0 to infinity. It just tells me that there is no contribution from the epsilon from the ground state. This epsilon is equal to 0 is the ground state. So there are no particles in the ground state. There's no weight. Well, you see, the ground state is just one state, so in general, for a classical or semi-classical system, we wouldn't expect any contribution from the ground state. So it's just one among millions or trillions of states. But the problem is when you look at the quantum mechanical systems, as you lower the temperature, most of the particles go to the ground state. So there can even be a macroscopic number of particles in the ground state. So that's practically we don't know. So we should somehow take that into account. In this expression, we are basically ignoring it. So what we will do is we will modify this relation, and I will just say that this is plus n0. So the number of particles in the ground state. So the integral gives 0 weight to the ground state. And this additional term is what we add as the number of particles in the ground state. Now, if you look at the average number of particles in the ground state, this is just 1 over z to the power minus 1 plus 1, or z over z plus 1. This is the number of particles in the ground state. And, well, let's see, we can solve for z n0, z plus n0 should be equal to z, or z is equal to n0. No, sorry, this is minus 1. Z is n0 over n0 plus 1. And if there are a macroscopic number of particles in the ground state, that is, if n0 is of the order of n, this basically becomes 1 minus 1 over n0. So this is basically our claim. You see, if you look at this number, if there are a macroscopic number of particles in the ground state, then z goes to 1. It's very close to 1. But z close to 1 means mu is very close to 0. And in fact, in the macroscopic thermodynamic limit, which is when our system size becomes infinitely large, n0 being of the order of n becomes infinitely large, and hence mu is exactly 0 in that limit. But if we don't go to the thermodynamic limit, mu is very close to 0, but not exactly 0. So this is n, the total number of particles. Now let's do a couple of things over here. So when does z or mu become very close to 1? You see, if you look at this expression over here, this is the number of particles in the ground state. So this is the number of particles in the excited states. This is the number of particles in the excited states. Now, let's just, let me rewrite this, also add this A epsilon. This is our A epsilon. Number of particles in the excited state is 2 pi v 2m to the power 3 halves divided by h cubed, integral from 0 to infinity, the epsilon to the 1/2 divided by z to the power minus 1 e to the power beta epsilon minus 1. Or let's just make a change of variable. Let me just define epsilon to be kt times x. So the number of particles in the excited states becomes 2 pi v 2m kt to the power 3 halves divided by h cubed from 0 to infinity, the x to the power 1/2 divided by z to the power minus 1 e to the power x minus 1. Now, whenever we are dealing with bosonic systems, you always get such integrals, and they are given a name, g nu of z. This is equal to, from 0 to infinity, dx x to the power nu minus 1 divided by z to the power minus 1 e to the power x minus 1, and let us divide by gamma nu. So the number of particles in the excited states we can write as 2 pi v 2 mkt to the power 3 halves divided by h cubed, and g 3 halves times of z times gamma 3 halves. So what is gamma 3 halves? Do you remember? This is an integer. Huh? Well, let us see. So it's a square root of pi over 2. So this is square root of pi over 2. So this whole thing becomes v times 2 pi mkt to the power 3 halves over h cubed g 3 halves z. Now this whole thing is what we had defined already as 1 over lambda cubed. So the density of excited particles times lambda cube should be equal to g 3 halves z. Now, what is this g function? Let's study those functions a bit. Now we can look at various limits. One of them will be what happens when g3 half. Well, let's look at an expansion of g3 half as a function of z. Well, this is equal to 1 over gamma of nu, 0 to infinity dx, x to the power nu minus 1, times z, e to the power minus x times z over 1 minus z e to the power minus x. So we can make a Taylor expansion around z is equal to 0. This is equal to 1 over gamma of nu, 0 to infinity dx, x to the power nu minus 1, e to the power minus x, z, and from 0 to infinity, z to the power n times e to the power minus nx, which is 1 over gamma nu, sum from n 0 to infinity, z to the power n plus 1, from 0 to infinity dx, x to the power nu minus 1, times e to the power minus n plus 1 of x. So let me make a change of variable. Let me just write x as y over n plus 1. So this function, g nu of z, is n from 0 to infinity, z to the power n plus 1, 1 over n plus 1 to the power nu, and gamma of nu. And I also have a 1 over gamma of nu. So this cancels this one. So it basically has a, let me write it in this form, n from 1 to infinity, z to the power n divided by n to the power nu. So this is z plus z squared divided by 2 to the power nu plus z cube divided by 3 to the power nu, no, z squared, z cubed plus etc. This is the expansion of g nu of z. Now in particular, g nu of 1 is n from 1 to infinity, 1 over n to the nu. This is nothing but the Riemann zeta function. So g 3/2 of 1 is zeta 3/2. Now another thing, if you look at these expansions, all these terms are positive. All those expansions. So g nu of z is actually a increasing function. Now let's look at the particular case. Let's define this gz for 3/2 to be integral of, in our case, we had x to the power 1/2 divided by z to the power minus 1 e to the power x minus 1, x from 0 to infinity, divided by gamma 3 over 2. And let's see how it looks. So it's an increasing function. That's what we actually expected. So g of 1 is 2.6. This is the value of the zeta function, 2.61. This is zeta 3/2. So basically we have checked our results. Oh, sorry, you don't see all the screen. So what does it all this means? Let's go back over here. This is what we had. Now, number of particles in the excited state was a v times v over lambda cube. Well, 1 over lambda cubed is this number over here. 2 pi mkt to the power 3/2 divided by h cubed g 3/2 of z, which is less than v times 2 pi mkt to the power 3/2 divided by h cubed zeta 3/2, because when I put z is equal to 1, that is the maximum value of g 3/2 z, and g 3/2 1 is this zeta function at 3/2. Now, one thing is, if you lower the temperature, the right-hand side gets smaller. And eventually at t equal to 0, it becomes 0. The left-hand side, right-hand side, sorry. Whereas the left-hand side is the number of particles in the excited state. The remaining should be in the ground state. So that's the critical temperature, let's say, when the number of particles in the excited states cannot accommodate all the particles, is determined by this condition. N is equal to v times 2 pi mkt c to the power 3/2 over h cubed zeta 3/2. This is what gives us the critical temperature. And the number of particles in the excited states is basically T over T critical to the power 3/2 G 3/2 of Z. And in fact, if T is less than Tc, Z is already 1. No, sorry, here, G3 half Z. Okay, this is the T critical. So I'm basically, no, okay. If you divide this number by this number, NE over N is T over T critical to the 3 half G3 half Z over zeta 3 halves. So I'm just taking this number, dividing it by this. So all these V and the 2 pi M, etc., they all cancel. So for T less than T critical, zeta is 1 in thermodynamic limit at least. So the number of particles in the excited state, the fraction of particles in the excited state, let's say, this is equal to T over Tc to the power 3 halves. So the number of particles in the ground state, the fraction of particles in the ground state is 1 minus T over Tc to the power 3 halves. So if you would plot the number of particles in the ground state as a function of T over Tc, when T is up to T is equal to Tc, when larger than the critical temperature, the number of particles in the ground state is negligible. As you lower the temperature, the ratio increases. So this is N0 over N. Whereas if you look at the number of particles in the excited state, for T larger than Tc, all the particles are in the excited state. The contribution of the ground state is negligible. Again, it's just one state among billions and billions. And then below Tc, the number of particles in the excited state, they just decrease. So this is how each one behaves as a function of the temperature. Now let's get the pressure. Well, we will consider basically two limiting cases. One, Z is 1, that is for T less than T critical, and when Z is, well, two limiting cases are easy to deal with, let's say. Z is much less than 1. Now, Z is much less than 1, or the high temperature limit should basically go to the classical limit. So let's first go to the classical limit. You see, first of all, the PV, the pressure, PV over KT, this was given by minus the sum of the single particle states of the logarithm of 1 minus Z e to power minus beta epsilon. This is what we had already seen when we were discussing the grand canonical ensemble. This is equal to, okay, first let's separate the contribution of the ground state. Now for the ground state, epsilon is equal to 0. This is minus logarithm of 1 minus Z minus the contribution of all the excited states. So it's essentially 0 to infinity, the epsilon, A epsilon, times logarithm of 1 minus Z e to power minus beta epsilon. Now you see we had already expressed Z in terms of the number of particles in the ground state. This is our z. So if you look at the first term, logarithm of 1 minus z is equal to the logarithm of 1 minus n0 over n0 plus 1, logarithm of minus the logarithm of n0 plus 1. And okay, so let's just write everything again. So PV, or P over KT, let's say, we are interested in the pressure. This is equal to minus or plus 1 over V logarithm of n0 plus 1 minus 0 to infinity d epsilon. Okay, A epsilon is this one. Times the logarithm of 1 minus z e to power minus beta epsilon. Or we had already divided by v, this goes to 0. Now if you look at the first term, in the thermodynamic limit, logarithm of n0 plus 1 times 1 over v, this is of the order of 1 over n logarithm of n. N0 is less than n, the number of particles in the ground state. V scales as n. So this term as a whole is a correction which is of the order of 1 over n, which is negligible. So we can just ignore it, whatever the value of z is. Now that is kind of expected because in the ground state there are no the particles don't have any energy. So they cannot really exert the pressure. So that the contribution of the first term is the contribution to the pressure from the particles in the ground state. Now they're not moving, so they cannot exert the pressure. So P over KT, this is equal to minus from 0 to infinity the epsilon 2 pi times 2m to the power 3 halves divided by h cubed, epsilon to the 1 half the logarithm of 1 minus z e to power minus beta epsilon. Now let me just do an integration by parts. So I can just convert this integral to an integral that we had already defined as g. So this is equal to minus 2 pi 2m to the 3 halves divided by h cubed, 0 to infinity, the epsilon. This is epsilon to the 3 halves. Its derivative with respect to epsilon. It will give me this epsilon to the 1 half, but it will also give me a factor 2/3. 3 halves, which I should cancel, is 2/3. And then the logarithm of 1 minus z e to power minus beta epsilon. So now I can do the integration by parts, P over KT. Okay, from the limits, I won't get any contribution, neither from 0 nor from infinity. And so this is equal to 4 pi 2m to the 3 halves over 3h cubed from 0 to infinity the epsilon to the 3 halves. If I take the derivative with respect to epsilon, I get z beta e to the power minus beta epsilon divided by 1 minus z e to the power minus beta epsilon. This is equal to 4 pi 2m to the power 3 halves divided by 3h cubed from 0 to infinity the epsilon to the power 3 halves. I can also take the beta out, 1 over z to the power minus 1 e to the power beta epsilon minus 1. That's just like the number of expression, the integral appearing in the number expression. The only difference is instead of epsilon to the power 1/2, I have epsilon to the power 3/2. Then I just redefine the variable beta epsilon as x. So this is 4 pi times 2m to the power 3/2 beta divided by 3h cubed, 1 over beta to the power 5/2 gamma 5/2 g 5/2 of z. This is the pressure of my system. Well, let me just simplify it a bit. Gamma of 5/2 is just 3/2 gamma of 3/2, which we had just said that it is square root of pi over 2. So this, I have 3 over 4 over here, 4 over 3 over here, they will just cancel. P over kt is, there's a pi, 2 pi m to the power 3/2 divided by h cubed. Now here kt to the power 3/2 and g 5/2 of z, or P is kt over lambda cubed g 5/2 of z. This is the pressure of my system. This is valid whatever the temperature is. I didn't really make any assumption whether I meant the low temperature limit or the high temperature limit yet. Now let's see. Well, we can look at a couple of things. Let us look at what is the energy of my system. Now, the energy of my system, if you remember our discussions on the grand canonical ensemble, we said that this is the derivative with respect to beta, with a minus sign, of logarithm of the grand partition function, assuming z and v constant. Well, this is equal to minus derivative with respect to beta of the logarithm of the grand partition function was pv over kt. Again, I'm taking this derivative assuming z and v constant. Minus the derivative, okay, so let's do it slightly differently. Now, pv over kt. This is, in terms of beta, it's over here. Just multiply this expression by v. So basically it's proportional to beta to the power minus 3/2. So u is minus, well, if I take the derivative with respect to beta, it will bring a factor 3/2 and lower the power of beta by 1, so it's the same thing as dividing by beta. What remains will still be pv over kt. Now this beta cancels this kt, minus signs cancel, so we have this relation, pv is equal to 2/3 of u. This is valid for any boson system, for any boson gas. Again, up to this point I didn't make any assumption about the temperature. Whether I'm at low temperature or at high temperature, this is the same. It's also consistent with our understanding that ground state particles do not contribute to the pressure. Well, they also do not contribute to the energy, because their energy is zero. Okay, now let's go back. Let's see what we can say about the pressure as a function of temperature. First, let's look at the low temperature limit, below the critical temperature. Well, below the critical temperature, Z is just 1. So the pressure is equal to kT over lambda cube times a zeta 5 halves. Well, independent of volume. Now, this is also what we expect from a phase transition. You see, if you consider, for example, liquid vapor phase transition, you take a container, isolate it so that no gas can escape from it. If you put some liquid, then some of that liquid will evaporate and fill the empty region, and then this evaporation will continue until the vapor pressure is equal to the vapor pressure at that temperature. Now, if you try to compress your system, what will happen is that more gas will condense, but the pressure will stay the same. Pressure in a general phase transition is determined by the temperature only. If you increase the volume, so more liquid will evaporate. Again, eventually the pressure will be the same when the equilibrium is reached. So this is exactly the same phenomenon. So at low pressure, below the critical temperature, the pressure is constant. Now, for T larger than critical temperature, let's say much larger than the critical temperature, then Z, well, Z goes to 0. Z is small. Well, we had already had an expansion, you see, to determine the pressure. Whatever the value of Z is, this is the pressure. And for small z, this will be kT over lambda cube z plus z squared divided by 2 to the power 5 half plus z cube divided by 3 to the power 5 half, etc. Now the next question is, what is z? We have to determine z. Well, z is given in terms of the number of particles. You see, if you remember our previous expression for the number of particles, this is n over v. Since we are at high temperature, there is no particles in the ground state. All of them are in the excited state. So G3Z, 3 over 2Z, is just a lambda cube over V. Now, if we are at very low temperatures, so G3Z is approximately Z. So we just take the first term. So Z will be approximately lambda cubed over V. And if you just place it over here, see P is kt over lambda cube times z, which is lambda cube over v. Well, these cancel, and we have PV and KT is equal to PV. So we basically recovered the ideal gas law. Now, what happens if the temperature is high but not that high, or Z is very small but not that small? We have to take into account the higher corrections to here. Well, in order to do that, we have to basically solve this equation. Lambda cubed over V is equal to Z plus Z squared over 2 to the power 3 halves. So what is Z? Well, let's try to solve this. Z, we know that Z should be a function of lambda cubed over V. That's given. So let's consider an expansion of Z in terms of lambda cubed over V. And these ALs are what are called the virial coefficients. Well, let me just calculate this up to second order. So you see what, and if you want to go to higher order, it's just straightforward application of the same principle. So lambda cubed over V should be equal to Z, which is up to second order, A1 times, well, let me just call this delta. Let me not write it all the way constantly. Let me just call it delta for simplicity. This will be equal to Z, which is A1 times Z plus A2 times Z squared plus Z squared, which is A1 Z plus A2 Z squared divided by 2 to the power 3 halves. No, not Z, sorry, delta. Plus, of course, there are terms of the order of delta cube. So delta should be equal to A1 delta plus A2 plus A1 over 2 to the power 3 halves times delta squared plus terms that are of the order of delta cube. If you want to keep the delta cube terms, it's just straightforward. Now, we see this should hold for all values of delta, which basically tells me that A1 is equal to 1. A2 plus A1 over 2 to the power 3 halves should be equal to 0. Or A2 should be equal to minus 1 over 2 to the power 3 halves. Now I know what Z is as a function of lambda over V, lambda cubed over V. So Z up to this approximation, lambda cubed over V minus 1 over 2 to the power 3 halves lambda cubed over V squared. Of course, there are infinitely many terms over there. Now I can write the pressure. You see, the pressure was given by this expression. Again, I will just keep the Z squared term. this is our pressure. Now I also know what Z is. So this is equal to K2 over lambda cube. Now in Z squared, in Z I have lambda cubed over V minus 1 over 2 to the power 3 halves lambda cubed over V squared, plus in Z squared, the square of the first term is up to the order that I'm keeping, so it's 1 over 2 to the power 5 halves lambda cubed over V squared, plus of the order of delta cube. Or pressure is equal to Kt over lambda cube, lambda cubed over V 1 plus lambda cubed over V, that's a minus lambda cubed over V 1 over 2 to the power 5 halves. And this is the first correction to our ideal gas law. Well, the pressure of this gas is a bit smaller than the pressure of the ideal gas. Now, if you remember our previous discussions, we had said that, okay, but if you remember, we were looking at the, we studied the two particle density of states. And there we said that, okay, the bosons tend to get together, and the fermions tends to stay apart. Although there is no force between these particles, due to their quantum mechanical nature, we can define some kind of a quantum mechanical force, which is attractive for bosons and repulsive for fermions. Well, if you have an attractive force, you see, if you just imagine you put this system in a container, the pressure is on the walls of the container is created by the particles hitting the container. Well, if a particle is moving towards the wall, well, there's this attractive force, it will slow down. So the force it will exert will be smaller as it's moving towards the wall, because it's getting smaller, slower. So the pressure even from that quantum mechanical force interpretation, you would expect the pressure to become smaller, and that's indeed the case. Due to this quantum mechanical attraction between the bosons, the pressure is smaller. Now let's see what else we can see. We can look at their specific heats. Let's consider that one also. Now, to calculate the specific heat, we need the energy. Now, we had already calculated the energy. You see, if you go back, the energy of these particles is 3/2 PV. Well, this is 3/2 PV over KT times KT. And this is 3/2 logarithm of the grand partition function times KT. And PV over KT, we had already evaluated it. Basically, this expression is our PV over KT, P. And I said that this is valid for all the temperature. This is P over KT. Multiply this by V. So the energy of my system is just 3/2 2 pi m kt, or let me just rewrite it as, all of this is nothing but 1 over lambda cube. This is 3/2, this number is 1 over lambda cube, g 5/2 of z times kt. Times p. Now we can look at the specific heat at for temperatures below Tc. Now for temperatures below the critical temperature, Z is just 1. So the U is 3/2 V over lambda cube. G is zeta 5/2 times kT. This is proportional to T to the power 5/2. Well, Cv is nothing but du by dt. So this is equal to, lambda cube is T to the power 3/2, 1 over lambda cube. There is this kT, additional kT. So the whole thing is proportional to T to the power 5/2. Now if you take the derivative with respect to temperature, you get 5 over 2T times U. This is the specific heat, Cv, for T less than the critical temperature. Well, and this is proportional to T to the power 3/2. So Cv is a function of temperature. Just increases. So this is T over Tc. This is 1. As T to the power 3/2. Now we can look at the other extreme. For T much, much larger than Tc. So this is our U. Actually, we already have the pressure, right? No, I need to take this derivative. So, no, I have the pressure. You see, this is our expression for the pressure. I already know this expression. Let me use that one. And we already know that U is equal to three over 2 PV. 3 over 2. The pressure is this one. V times kT over V. 1 minus lambda cubed over V. 1 over 2 to the power 5/2. So let's see, U is equal to 3 over 2 nkt 1 minus lambda cubed over V 1 over 2 to the power 5/2. Specific heat is again du by dt at constant volume. So this is equal to 3 over 2 nk 1 minus lambda cubed over V 1 over 2 to the power 5/2 plus 3 over 2 nkt, the derivative of the parentheses. Well, keep in mind that lambda cube is proportional to t to the power minus 3 halves. So I have this minus 1 over v, 1 over 2 to the power of 5 halves. If I take the derivative, it will bring me a minus 1 over, it's proportional t to the power minus 3 halves, so minus 3 halves times lambda cubed over t. This t will cancel this t over there. So Cv over, let's say, Cv over n times k. This will be equal to 3 over 2 n times, I have already divided by n times k. 3 over 2, 1 minus lambda cubed over v, 1 over 2 to the power of 5 halves. Well, here I have this minus will cancel this minus sign, so I have a plus 9 over 4 lambda cube over v, 1 over 2 to the power of 5 halves, or 3 over 2 times 1 plus 1 over 2 lambda cubed over v, 1 over 2 to the power of 5 halves. Now the crucial thing over here, of course, plus of the order of that squared terms. The crucial thing is that it is larger than the classical limit. And as you lower the temperature, lambda is increasing and it gets larger and larger as you lower the temperature. So if you just combine these two results, T over Tc, this is the classical value, let's say this is, let's put 1 over here. So this is a plot of Cv over 3 over 2 nk. Now on one hand we had seen that below Tc it increases linearly. It starts from 0 and increases, not linearly, but as a power law. Above Tc, we know that asymptotically it goes to the classical value, but it doesn't go down, it goes up from the classical value as you lower the temperature. Now what happens is here you get a cusp. The derivative is not continuous at the t is equal to Tc. Well, this is kind of a prediction of our formalism. Now, do we observe it? Well, yes, we did almost observe it, let's say. Now we have a system of Bose-Einsteins, weakly interacting bosons we can create by helium. Helium that's one of the reasons why it's so popular in these Bose-Einstein condensates. Being an inert gas, it doesn't really interact with each other. Their interaction between each other is very small, and at low enough temperatures they do form a Bose-Einstein condensate. And we can measure the specific heat. And the specific heat, it turns out, has this form. Not exactly of the same form. It's not so symmetric. So this is why it's called the lambda transition. It looks like the letter lambda. In helium-4. Well, the reason why it's not really doesn't really have our predicted shape is, you see, when we were dealing with the boson gas, when we obtained this plot, what we had is, it's actually, we had a gas of non-interacting systems put in some volume. Within the volume, there's no force acting on them. But if you want to keep helium and cool it down, most of the time what you do is you just I mean, this cooling at such low temperatures, you cannot really just get a container, put your system in the container, and then just turn a knob and it becomes cooler. So what is usually done is called laser cooling. Now in this laser cooling, what you do is, so you have your atoms, it has their energy levels. You shoot some laser whose frequency is adjusted so that it's just below one of the transition energies. It's not exactly at the transition energy, but it's below the transition energy. So what happens is, if an atom is moving towards your laser beam, then in its rest frame the frequency is slightly higher, so it can excite the atom. So if the atom is moving towards your beam, it gets excited. Once it is excited, it will emit the radiation, but it absorbs this light from a particular direction, but when it emits it emits in every direction. So basically it will be losing momentum during this emission and absorption. And of course, to do the system, you have to suspend them with some potential, etc. You create a trap so that it doesn't interact with anything else. So if you put a container, it will absorb heat from the container also. That's also not something that you want. You want it to be isolated almost completely. So you just create a trap by laser beams, and then cool it again by laser beams. But the trap is a potential. So if you just consider a harmonic trap, now the energy levels will be given by h bar omega, let's say 1 L1 plus h bar omega 2 L2 if it's not symmetric. These are the energy levels, ignoring the ground state energy, because up to now we always shifted our energy level so that the ground state is at zero energy. Now you can repeat almost all the previous treatment, but first you need to identify what is A of epsilon. What is the density of states for such a harmonic trap? Well, you see, what was the A of epsilon is the density of states of particles that have energy epsilon. Well, the energy, if you convert the L summations over integrations, the L1 of, I only want the values L1, L2, and L3 such that the energy level is actually epsilon. This will be our smooth density of states. Because actually the actual density of states will be just a sum of Dirac deltas, but if you just smooth them out, and due to all this residual thermal motion, etc., the finite size of the system, what you will observe will be a smoothed out version of the density of states. This is your density of states. And this turns out to be proportional to epsilon squared. And if you take this difference into account, then a density of states that's proportional to epsilon squared and do all the derivation of the specific heats, you do get this graph. So, okay, in the helium gas, it's not the completely isolated non-interacting bosons. There is external potential, and that external potential is basically the cause of this deviation in the CV from what we had predicted to what we had actually observed. Now let's look at what else we can study. Adiabatic curves. our ideal boson system. Well, first of all, we need to find the entropy to study the adiabatic curve. So if we know on which parameters and how entropy depends on those parameters, if we determine those, then we can say how they should vary in order to keep entropy constant. And to do that, let's just, okay, we had already calculated U. And U minus Ts plus PV was equal to mu times N. Do you know how to derive this relation, by the way? Do you know how to derive this relation?
This one? From E?
Yeah, I mean, you just look at, you can look at U minus Ts plus PV. This will be minus SDT plus VDP plus mu dN. But this should be an extensive quantity, and the only extensive parameter appearing over here is n. So this combination has to be proportional to n, and the proportionality constant just turns out to be mu, because if you take the derivative with respect to n, you should get mu. And that gives you this one. By the way, we said that for boson systems, mu is negative. But at the same time, this was the definition of mu. So it's the increase in the energy if you add one more particle to the system. How come that increase is negative? How should you interpret that? You see, if you look at this EU, our thermodynamic relationship, mu is the increase in the internal energy of the system when you add one more particle to the system, and the n is 1. And for bosons, this mu turns out to be negative. So you add one more particle, then the internal energy is decreasing. How come? Does this make sense? What kind of sense should we make out of this?
If mu is negative,
You see, if you have a system, I'm adding one more particle, that particle has an energy.
But it has a negative energy.
What does it mean? I mean, the energy of a particle is, the only energy we are treating, at least up to here, is the kinetic energy, which is always positive, right? So you are adding a particle, so its kinetic energy is positive, so its energy is positive. So I would have expected the mu to be positive. Ignoring any interaction. The interactions can have negative potential energies. If you ignore any interactions, then the mu should be positive, no? You see, the thing that I'm kind of misguiding you is that I'm adding one particle, but there are constraints on how I am adding that particle. I'm keeping the volume fixed. Okay, that doesn't really change my argument, but I'm also keeping entropy fixed. Entropy depends on the number of particles and the energy of my system. If I add one more particle, I'm increasing the entropy also. If I don't do anything else, just adding one particle to my system, it will increase the energy and it will increase the entropy of the system, because the energy of the system, it will increase the energy because the particle has a kinetic energy. It will increase the entropy because now I have more energy that can be distributed in more ways to more number of particles. So in order to keep the entropy, as I'm adding my particle, I have to extract some energy from the system, so that at the end of the day, the energy of the system will be lowered. So that's why the chemical potential is negative, at least for bosons. We will see that for fermions, the chemical potential can be positive. There is no restriction. Anyway, if we come back over here, so this is what we have. So U minus Ts plus PV is equal to mu n. This tells me that S is given by U plus PV over T minus mu n over T. This is my entropy. So we had also seen that U was it 2/3 or 3/2? U is 3/2 PV. So this is 5/2 PV over T minus mu n over T. Now PV over, this is 5/2. No, sorry, this is not U, this is S. Five half PV over T minus mu n over T. Now we had already calculating these properties. Okay, so this is the P. So S is equal to 5/2. PV over T will be K over lambda cube G 5/2 Z minus mu n over T. Or let's just say S over K. There's a V over here. Did I miss anything? No. This is my entropy expression. Well, we can look at various limits. One is T less than Tc. Well, let's see, even this expression might be enough for us. So S over N, entropy per particle. This is 5/2 V over lambda cube G 5/2 of Z minus, well, mu over KT is nothing but logarithm of Z. Remember, Z is e to the power mu over KT. This is the S over N. And furthermore, how do you determine the Z? Well, G 3/2 of Z is equal to V over lambda cube. So you see, the entropy is, I can write it as a function of V over lambda cubed only. This tells me that S is some n times some function of V over lambda cubed, whatever the temperature is for a bosonic, non-interacting bosonic system. So adiabatic process, S is constant. Basically, it tells me that V over lambda cube is constant. Or this tells me that V times T to the power 3/2 is constant. This is for an ideal gas. Well, we can look at the for T larger than Tc. You see, we had already obtained the expression for the pressure. Or let's see. Now for T less than Tc. You see, of course, the pressure is, then Z is 1, then pressure is kind of independent of the volume. But if you are changing your system in an adiabatic wave, you have to, we can just say that P is proportional to T to the power 5 halves. We already know that V times T to the power 3 halves should be constant in an adiabatic process, whatever the temperature is. So V to the power, let's say, 5/3 times T to the power 5 halves. This is constant. I'm just taking the 5th power and the square root of that expression. No, I'm just taking the to the power of 5/3. So since pressure is proportional to T to the power 5 halves, so this just tells me that P times V to the power 5/3, this is constant for a Bose-Einstein condensate. Well, in an adiabatic process, as you change the volume, you have to change the temperature. As you are changing temperature, you are basically changing the pressure for the Bose-Einstein condensate. And you have to do that in such a way that PV to the 5/3 should be a constant. Yeah, this just looks like the ideal gas. But just one note, in this case, 5/3 is not equal to in the ideal gas, classical ideal gas, 5/3 was equal to Cp over Cv, which was defined as the gamma. In the Bose-Einstein condensate, again we have the same power, but keep in mind that Cp and Cv for the Bose-Einstein gas are different than what we had for the ideal gas. And if you take the ratio, it's not a constant. But nevertheless, Cp in an adiabatic process, PV to the 5/3 is still a constant for the Bose-Einstein condensate. About the transition temperature, well, the dependence of the pressure on temperature is a bit more complicated, so we cannot really obtain such a simple relation. And what else would you like to know about the Bose-Einstein condensates? Well, basically this. You can look at the isothermal curves. Pressure as a function of temperature. Now pressure as a function of volume. You see, until okay, this is the, no. In a Bose-Einstein condensate, we know that pressure depends only on the temperature. So if you have an isothermal curve, in an isothermal curve, the pressure will be just a constant, since the temperature does not change. But of course, if you increase the volume, if you go back to our criteria for the Bose-Einstein condensate, so this is our criteria for the Bose-Einstein condensates. This was the criteria. So at a fixed N and V, this gave us the critical temperature. But if we are looking at the isotherms, we are basically, we will have various values of temperatures, but then we will have some critical volume. If the volume is too small, then you have a Bose-Einstein condensate, because some of them has to be pushed to the ground state. So so this is at a given temperature. This is what defines the critical volume. Above this volume, the pressure will not be constant, because all of the Bose-Einstein condensate has evaporated. So the pressure will drop. If you start at a higher temperature, this condition will be satisfied for a smaller value of V, and then you will have a Bose-Einstein condensate starting from this value of V. I said if this is P1, this is P2, here we have V critical 1 with V critical 2. Above this value, you have a Bose-Einstein condensate. You don't have a Bose-Einstein condensate anymore. Now, if you look at all these points, they have such a curve. On the left-hand side, you have a mixture. Of the Bose-Einstein condensate and the normal phase. You see, what we call the Bose-Einstein condensate are the particles in the ground state. Not all the particles, as long as you don't go to the zero temperature, not all the particles are in the ground state. It's just a macroscopic number are in the ground state. So there's a mixture. On the right-hand side, you have just the normal phase. And that's practically all we will be discussing about the Bose-Einstein condensate. So if we leave aside all the technical details, so what is actually happening over here is as you lower the system, as you lower the temperature of your system, it is possible that a macroscopic number of particles are in your ground state. But this doesn't always happen. Here we were looking at a non-relativistic gas in 3 dimensions. For example, in 2 dimensions you don't get a Bose-Einstein condensate. The transition temperature turns out to be 0. So there's no Bose-Einstein condensations, unless you apply some external potential to the system. But at least in this system, in the non-relativistic 3-dimensional gas, below a critical temperature, you get this a macroscopic number accumulated in the ground state. And if you look at in the book, it's just like the condensation of water, but not in coordinate space, but in phase space. So it's basically all the particles have the same momentum. In the coordinate space, if you have a condensation, all the water molecules are collected at a given point. So that's what we call the condensation in coordinate space. But these Bose-Einstein condensates, they connect at the same point in phase space. They have the same wave function, they are all in the ground state, etc. Now, what is happening here is the criteria for the appearance of the critical temperature, at the critical temperature, basically the thermal wavelength becomes comparable to the separation between the atoms. So the atoms actually do start overlapping. So it's no longer possible to distinguish the atoms. So it just acts as a one collective mode. They also have the same wave function. Now the rest are the technical details that you can just derive by applying the standard statistical mechanics concepts. Okay, questions? Do you remember when is our final exam? Okay, we'll see. Probably we will have one more in-class exam and one take-home. I'm thinking of maybe on Tuesday, the last day of the classes, we can have the second midterm in class. And then on our final date, we will have this take-home, or we can postpone the final towards the end of the final period. Any questions? So see you tomorrow. And tomorrow we will be starting with the fermionic systems.